Hey everyone. So today, lesson 5, as promised, we're going to focus still on laws of logarithms, but with respect to logarithmic equations instead of exponential equations. The note itself isn't as long as it was yesterday. Like there's not as many examples to go through, but there will be lots for you to practice in homework for this one. So just take note of that. Okay, so just a quick intro here. Last class we figured out how to solve exponential equations using logarithms. Generally speaking, when we have an unknown exponent and we can't make the bases the same, we convert to a logarithm. Just as an aside there, you do always want to try and make the bases the same first. That is usually the better method to try. We only do what we did yesterday if we can't make the bases the same. Now, today, if the unknown is in our logarithmic function, we may have to convert to an exponential. So it's like we're just doing everything we did yesterday, but in reverse, okay? So, first question, solve the following algebraically and state the domain. Now, we gotta think about restrictions. Remember that you can't take the log of a negative number. So as soon as you see this x right here, there are restrictions on that x because I can't take the log of a negative number. So we would have to say x is greater than 0. Now, saying that, that is also, remember we had this conversation once where we said the restrictions often become the domain of the graph. The restrictions on a radical became the domain of that radical. The restrictions on the rational became the domain of that rational. So it's the same thing here. If you're asked for the domain, you're really just asked to think about the restrictions. Because x has to be greater than 0, you know that the domain for this guy will be x is greater than 0 and x is a member of the reals. Now, to solve, I need to try and get the log x all by itself. And then once I have it all by itself, I can convert it to exponential form. So I'm going to subtract 5, I'm going to divide by 3. If I subtract 5, I'll have 3 on this guy, divide by 3, and I'll have 1. What base is this? It's base 10. So if I was now to convert this to exponential form, the base becomes the base. The dude that was locked, which is the x right now, will be free, which is the point right now. And then the dude that was free will be locked. So that's going to be x equals 10 to the 1. Now 10 to the 1 is just 10. So x equals 10. And that's my answer for the first guy. And the second guy, we always kind of want to do the same thing. If we need to get rid of the log, we need to switch to exponential form. But you can't switch from log form to exponential form when there's more than one log happening at the same time. So that's where your other power log laws come into play. We need to squish these logs together. So we have two different logs that have the same base, and we're adding those logs together. Your log laws state that I can write that as a single logarithm if I multiply the x and the 4x together. So x times 4x would give me 4x squared. Oh, sorry, I forgot about the domain. Again, I can't take the log of a negative number, so x has to be greater than 0. And so then putting these together as a single logarithm would be log base 5 of 4x squared. X times x is x squared equals 125. Now I'm ready to convert this to exponential form, and I can solve from there. So base is 5, so I'm looking at 5 to the 125 equals 4x squared. Now if I want x by itself, I'll divide both sides by 4, and then I'll square root it. Now, square rooting this, I'll have a 2 on the bottom. This is like 5 to the 125 to the 1/2. So I'll just write that as 5 to the 125 over 2. Now, taking the square root, technically it could be positive or negative, but according to the domain you just gave me, I can only have the positive, so I'm only going to state the positive right now. So x equals 5 to the 125 over 2 all over 2. And I'm just going to leave it like that. That is my exact value answer. If I was to put that in a calculator right now, I would get a decimal approximation, and I was not told any rounding instructions. So, okay. Next example, we have log base 3 of x minus 2 equals log base 3 of 3x plus 2. Now, there are two different logs here that we have to think about restrictions for. This guy here tells me x has to be greater than 2. this guy here tells me x has to be greater than -2/3. Now, if you're trying to figure out where I'm getting those, I'm just setting that equal to, well, I'm setting that x minus 2 greater than 0. So I'm going in my head, and if you want to do it on paper, that's totally fine. But I'm going x minus 2 has to be greater than 0, so x has to be greater than 2. And then I'm going 3x plus 2 has to be greater than 0. Bring my 2 over, that's where the negative comes from, and then divide by 3. So 3x is greater than 2, and x is greater than -2/3. Sorry, I forgot my negative there. Okay, now though, you have some thought to have. I don't need to write both of these restrictions. If x has to be greater than 2, I actually don't care that x has to be greater than -2/3. The fact that x has to be greater than -2/3 there doesn't really matter, because x is greater than 2 is more restrictive, okay? So you want to go with the more restrictive one, which is x is greater than 2. So your domain here will be x is greater than 2. Now, we had a similar situation like this yesterday with exponents. Again, this is the common thought I need you to have here. If log base 3 of something equals log base 3 of something, my somethings have to be the same. So at this stage, I can just pull the somethings out. I know that x minus 2 has to be 3x plus 2, and then I can just algebraically solve. So I subtracted x from both sides, subtracted 2 from both sides, and x ends up being -2. Now, I have to always check my solution against what my domain or what my original restrictions were. We have been told that x has to be greater than 2, which means this is no good. That's an extraneous solution. There is no solution here. Okay? Okay, now in the next one, I want you to notice I can't just pull this out. I can't just pull the x and the x plus 2 out like I did in that last example because of this 3. This 3 is in the way now. So I need to look at it the other way. I need to try and put all my logs on one side of the equation. I need to use log laws to combine those into a single log. Then I need to switch to exponential form. So let's talk about restrictions first. I know that x has to be greater than 0 here, and I know that x has to be greater than -2 on the other side. So who wins here? Who's the more restrictive statement? The greater than 0 is. So my domain will be x is greater than 0, where x is a member of the reals. Now I want to bring this whole term over here so that I've got all my logs on one side. So I essentially add that to both sides, and then I'm left with just 3 on the other side. Now I want to try and combine these two logs together. When we are adding logs of the same base, they can be written as a single logarithm if I multiply the things I was taking the log of. So I just have to multiply x times x plus 2, which is going to give me x squared plus 2x. Okay, now I'm ready to convert. Because I have a single log here, I'm ready to convert to exponential form. So this will become x squared plus 2x by itself, and it will equal 2 to the 3. Well, now I just got a cute little quadratic. 2 to the 3 is 8. I'll bring my 8 over to the other side so that it equals 0, and I'll try and factor it. Two numbers that multiply together to give you -8 and add together to give you 2 are -2 and 4. So that means x equals 2 and x equals -4. Now, if I go back to my restrictions, x has to be greater than 0, which means I can't have the -4. So my final answer is x equals 2. It is super important when you're showing your work here though. Show that x can equal -4 and 2 first, and then show that you understand -4 is bogus. Somehow scratch it out, call it extraneous, whatever you want to do. And then conclude somehow that you know the only answer possible here is x plus 2. Okay, now in the next two examples, a couple of things to talk about. The unknown is actually the base, which is okay. This is going to feel familiar, but the one thing you need to think about here is the domain. As far as bases of logs go, they have to be greater than 0, and they also can't be 1. So your domain becomes x is greater than 0, but x can't be 1, and then x is a member of the reals. This is already in a single log form, so I'm going to switch it right away to exponential form. Base becomes the base. Dude who was free will now be locked in as the exponent. Dude that was locked will now be free. So that's going to be written as 3 equals x to the 5/6. Now, we did an example like this in our last note. If we want to try and get rid of that exponent of 5/6, we really just take it to another power. We take it to the reciprocal. So I'm going to take both sides to the 6/5. That will give me just x here. It'll give me x to the 1, which is x. And then I'm left with 3 to the 6/5 on the other side, which I'll just leave as the exact value answer. Okay, another one similar to that. We just have a few other things to do there because of the 4 in the front. But first, the domain, again, x is greater than 0 and it can't be 1. I'm going to divide both sides by 4, so 2/4 gives me a half. So I'll end up with log base x of a half equals a half. Switch to exponential form, so I've got x to the half equals the half. Now, if I want to get rid of an exponent of a half, I'll take it both, essentially we'll square both sides. So 1/2 squared is 1/4, so x equals 1/4. Okay, now be careful with this guy. Lots of us want to look at this and say, oh, that 2 can come right to the front. We talked about this yesterday. This is a different situation. This is not log of x squared, it's log of x all squared, and that's different. You need to look at this more like a factoring question. You're gonna bring the log x that's on the right side over so that it equals 0, and then you can factor out a log x, okay? So my domain is greater than 0. I'm gonna bring that log x over, factor out a log x. So now this is the 0 product principle. I've got log x and I've got log x minus 1. So either log x equals 0, and if that's the case, remember my base here is 10, so x will equal 10 to the 0, which is 1. Or I take this guy and say, okay, log x equals 1. Switching to exponential form, that would be x equals 10 to the 1, which would be 10. Both of those are allowed within my domain, so this guy has 2 solutions. And then this guy, again, I want you to look at this and see that it's more like a factoring question. I'm looking for 2 numbers that multiply together to give you -5 and add together to give you -4. If you would prefer to make a substitution here and say let log x equal a and then rewrite it as a squared minus 4a minus 5 and solve it that way, that's totally okay. Just remember, you have to say that you're doing that substitution. So I have to see somewhere in your work, let a equal log x or whatever, okay? I'm not gonna do that. I'm gonna leave it as it is, and I'm just gonna factor it. So 2 numbers that multiply together to give me -5, add together to give me -1 would be -5 and +1. My domain here is greater than 0. Okay, so this guy tells me log x equals 5. If I was gonna switch this to exponential form, that would be x equals 10 to the 5, and 10 to the 5 is 100,000. And then this guy tells me log x equals -1. Be careful with this guy. I have had students in the past tell me right away, oh, I can't do that, it can't be negative. X can't be negative. This is not x being negative, this is log x being negative. If I convert that to exponential form now, that's actually 10 to the -1. 10 to the -1 is 1/10. That's still a positive number. That's still within your domain. Still perfectly okay. Okay, so there are 2 solutions here. X equals 100,000 and x equals 1/10. The last example to try together is a complicated one. It's messy because we've got multiple things happening. As far as the domain goes though, x has to be greater than 0. Sorry, that was not right. The x can be anything here because it's in, and we're not in a log anymore. We're in an exponent. So x is number of reals. Okay, I'm going to try and simplify this a bit. I'm going to divide both sides by 2,000. That would give me 1.02 to the x equals 3. 6,000 divided by 2,000 gives me 3. I'm now going to take the log of both sides. So all of that should sound familiar to you. Here's where it gets a little different. There's 2 terms going on here. So what I'm now going to do is I'm actually going to expand that out using my log laws. that'll be log 3 plus log 0.87 to the x. So that will look like this. Now, I want to get all the terms, just like I was doing yesterday, I want to get all the terms involving x over to one side and all the terms that don't involve x onto the other side. So I'm going to take that log 0.87 to the x here and bring it over. Before I did that, I just brought the x's to the front. I'm using my power log law, okay? We talked about that guy yesterday. I just brought that x over here, and I brought that x over here. Now I'm going to bring it over, so I'm going to subtract this guy from both sides, essentially. Let me get rid of that ink for you. Okay, now, this x can now be factored out because it's common to both terms. This is a subtraction of logs, so I could actually combine that together to be 1.02 divided by 0.87. Now, if I don't really want to write 1.02 divided by 0.87 though, I'd rather put that in my calculator and ask my calculator to give that to me as a fraction, which is 34 over 29. So now I'm looking at x times log 34 over 29 equals log 3. If I wanted x by itself, I could divide both sides by log 34 over 29. And then I could say, hey, we talked about the change of base identity there. We could just now write that as this is actually log base 34 over 29 of 3. So I'm actually going to write that in a kind of a simpler form and call it log base 34 over 29 to the 3. Okay? So that one was a little bit more complicated, but really nothing new to you. It was a bunch of steps that you had to do all together. Okay. All right, awesome. So in our summary, couple things just to keep in mind when solving a logarithmic equation algebraically. Start by applying the laws of logarithms to express one side or both sides of the equation as a single logarithm. If you get one side as a single logarithm, then you would switch to exponential form. If you get both sides as a single logarithm, remember there can't be an additional term there, but if both sides are a single logarithm, then you can just pull out the things you were taking the log of and solve from there. The logarithm of 0 or negative is undefined, so you always got to think about restrictions there. Whatever you're taking the log of has to be greater than 0. To identify whether a root is extraneous, substitute the root, substitute your answer essentially, into the original equation and check whether all the logarithms are defined. Or, what I think would be the easier way to do is check your answer against your variable. So if you always start by getting those variable restrictions, then when you get down to an answer, just check and make sure you're not in a restricted zone. You can solve an exponential equation algebraically by taking logarithms of both sides of the equation, then applying the laws of logs. When solving exponential equations, your first goal would be to try and make the bases the same. If that doesn't work, then you should go to taking a logarithm of both sides, or if you can, just switch it to log form. Sometimes that's easier too. So kind of the three-tier hierarchy of this is you would try, can I get the bases the same first? No. Okay, can I write it, can I write it as one log? So can I just take an exponential equation and convert it to a log equation? And then if I can't do that, that's when I'd now be looking at, okay, now I'm going to take the log of both sides. That shortcut method, that was kind of my tier 2 there. Doesn't always work. It gets much more messy if you were to try it when there's equations going on both sides. So just be careful of that. But again, this is that shortcut switching from logarithmic form to exponential form. And again, before I let you go, I just want to make the point, this and this are the exact same thing. Okay, all we have done is switched forms. There is no difference between those two items. They mean the exact same thing. Okay? All right, so now your job, I'm just going to clear that ink, your job will be to take it up to 322 which is a fair amount of practice. So give yourself some time. Make sure you're checking the answers on D2L. And if you do have any questions, please connect with me. In the meantime, have a fantastic day. Take care, guys.